welcoming Brett Maurer, who's an associate prof here at the UW in CE. And Brett has been a great partner in crime for thinking about compounding hazard between climate and tectonic phenomena. And Brett has had many recognition national-wise, awards for teaching, research, and education. I can't list them all. Data sets also to speak on the AI contribution that Brett had. So today we're going to have a very interesting talk, I think, about coming out of the graveyard from AI. So curious.
Yeah, so about the graveyard, I thought about how I might fit in the story being told today. And healthy teams and organizations, they have people that are pushing the boundaries, living in the clouds, and they have people who maintain order and they ground everyone else to reality. And when I looked at the lineup, I didn't see anyone who I thought would be very grumpy. And so I thought, well, I'll take one for the team and I'll play the part, at least momentarily. So to start, though, let me just state what is obvious, which is that geosystems are subject to numerous geohazards, and they're exacerbated and they're made more difficult to predict by weather extremes and climate trends. And so just a few would obviously be flooding and erosion on rivers and coasts, tsunamis, landslides, rockfall, debris flow, both from earthquakes and rainfall, superstructure damage from wind and ground shaking, the thawing of permafrost, fault surface rupture, volcanic eruptions, all the different manifestations, and soil liquefaction. And the story that I'm going to tell, I could tell about a number of these different geohazards. So for consistent context, I'm going to focus on one, and I'm going to choose liquefaction. If you're not familiar with it, it occurs in soil that is loose, saturated, and cohesionless. If you shake these soils, they will densify so rapidly that the fluid in the pores of the soil cannot escape. It will come under very high pressure, and that pressure will counteract gravity. And so effectively, the soil has no confining stress, hence it has no shear strength, and so it's like liquid, hence liquefaction. The effects of liquefaction are broad, and nothing is immune to it, and so it affects roads, ports, bridges, buildings, runways, rail, utilities, all matter of pipelines and lifelines. And we see earthquakes where it's responsible for more damage than any other earthquake effect. These are some before and after photos from Christchurch. This played out over and over in dozens of suburbs, 8,000 residential homes, all lost to liquefaction, 3/4 of the central business district gone. We have some very crude simulations of M9 earthquakes in Washington, and they suggest maybe a similar story. Homeland Security put out this report. They looked only at infrastructure owned by Washington State. That's not very much. And they said 3,000 kilometers of road, 2,000 kilometers of rail, 800 bridges, 8 ports, all out of service due mostly to liquefaction. And so, well, it's something worth trying to predict. And people do, and that takes me to the graveyard. So if we look at the AI spectrum, we're obviously somewhere between narrow and general intelligence, or AGI. And some people define AGI as, we'll know when we're there when we see skilled jobs broadly replaced. And I think certainly when you look in certain sectors, it does seem like it's on the horizon. But when I ask the alumni of our program in civil engineering, so these are people who, they run the biggest infrastructure consulting firms, infrastructure agencies in Washington, do you think you're going to be replaced by AI? Do you think your entry-level workers will? And they tend to say, no way. Then when I ask, well, how about narrow AI? Is there any narrow AI in your domain-specific work? And they can't come up with any. And frankly, neither can I. And so I'm not talking about the sort of narrow AI that's all around us, the Google, the GPT. I'm talking about the models you use to do real stuff. And so I noticed this, and a couple of years ago I wrote this paper, and I could have written it about other problems. Again, I chose liquefaction. So what I noticed that was strange was we got to this point where most liquefaction models in the literature use AI. I read 75 papers to write this paper, and what's strange is they're totally ignored. So for some context, one state of practice model, it's all mechanics, there's no AI, 150 citations per year in the literature, thousands of citations per year in consulting reports. These 75 AI models, 2 citations per year, no use in practice, no building code, design manual, textbook, even mentions that they exist. The preeminent textbook in our field, it was just updated. It's 1,000 pages long. AI doesn't appear a single time. And so if we're on the verge of AGI, you certainly wouldn't know it here. And so I think there's good reasons for why these models are ignored. And so I set out to try to explain why. And so my thesis is this. So most models end up in the graveyard. I'm going to quickly share 5 lessons in a very broad way, which is to say, I will say nothing about liquefaction or mechanics. So these will just be like very vague lessons, purposely vague. So number 1, it goes without saying that in practical fields, if practitioners are going to adopt AI, it better be proven against models they trust and are backed by consensus and are transparent, et cetera, et cetera. So when we look at the 75 papers and we ask, is the AI tested against a state of practice or SOP model, only 1/3 of them did. And so lesson 1, if AI isn't shown to be better than something simple, no one's going to risk using it. There's too much at stake, reputationally, legally, ethically. Number 2, there's so many bad practices because we have domain experts using AI and they don't understand AI. Or we have AI experts with no domain expertise and the result is also bad. So there's a lot of these bad practices. One of them that everyone is familiar with is overfitting. And so I see a lot of liquefaction models that claim to be 100% efficient. And that's really eye-opening. It sounds good, but it's terrible because people have dedicated their lives to predicting liquefaction, and the best they can do is like 80% efficiency. And so if I see 100, I know something is very wrong. And when you look at the papers in detail, they just make the most egregious of mistakes, like there is no test set. I mean, really bad stuff. And so lesson 2, a lot of AI, frankly, is done poorly, and I think you need to convince the reader that yours isn't. Number 3, I think we have to ask why AI should be useful. A lot of stuff out there is just predicated on the fact that it's impressive, and it is, but that's not enough. And so I see a lot of people developing geohazard models where they strip out all of the mechanics and the human knowledge, and they simply train on observations. And yes, AI can rediscover the mechanics. It can learn that from outcomes, but this tends to be a data-poor field. We don't have enough data. You cannot expect AI to do better when you are throwing out 50 years of lab testing, hundreds of millions of data points from physics-based simulations, et cetera, et cetera. So lesson 3, a lot of AI really lacks utility, and I think you have to prove at the onset why it should be useful. Number 4, I call quantum spookiness, to kind of misuse a term. And here I'm talking about the language barrier. So there's so much language complexity. This is how one abstract started. I won't read it. There's nothing technically wrong with this. The point is, does the practicing engineer know what this means? And probably not. There's so many different workflows in AI, right? We all know that there's just an endless array of things you could do to train a model. And each variant, you can call it something different and you can give it a unique name. And so we're looking at liquefaction models, but we see the models, they're said to be inspired by bees, ants, wolves, other bugs, and whales. And all of this I kind of jokingly call woo-woo. And I think that this is giving the impression to reviewers and editors who don't understand it that something more innovative is taking place than actual. And if you kind of peel back the veil of complexity, you often realize that what's left is kind of underwhelming in its novelty. And so lesson 4, if you don't convince the day-to-day practicing engineer why this is useful, they're not going to use it. So the final lesson, AI models have to be given as code, put in interfaces, somehow pre-computed and stored. Otherwise, no one can use them, obviously. So we look at the 75 papers. Is there any way to execute the model? Only 13% was a yes. 3% said they'd give it on request. I requested it, they didn't give it. So it is somehow the norm to describe AI models without giving them. And, you know, lesson 5, if there isn't somehow a model, if it doesn't really exist, no one's going to use it, and I'm not sure that you're really contributing to scientific process. So the outcome, as far as I can tell, at least in my very practical field, is a lot of people dismiss AI. And so I have colleagues who will sort of preach, stay away from AI. Like, there's no intellectual merit. There's no mechanics. It's a mistake. But then they'll turn around and they'll use empirical models. And like, there's obviously something wrong with this kind of way of thinking. But I feel like in contrast to this AGI on the horizon narrative in society, in some fields, AI has very negative connotations. And so I think if our hazard models are going to be used for good, we actually have to resurrect the reputation of narrow AI, because at least in my field, the literature is kind of a disaster. So that's the end of my grumpiness. I'll be a little bit optimistic now. So we've been trying to draw from these lessons and improve regional scale hazard assessment of infrastructure. And we're looking specifically at ground motions, landslides, and liquefaction. So again, I'll focus on liquefaction. And you know, in a perfect world, we would predict it within seconds of an earthquake occurring, at the resolution of buildings and properties, and over the broad extent of energy systems. The problem is our state of practice mechanistic models need site-specific data. And so at regional scales, I think the problem is less how will the material respond, and it's actually more what is the material. I'm not saying our models are perfect, they're not, but we have nothing to put into the model. And so that's what I'm focusing on in a lot of my work. So with a site-specific model, most of these models use something called a cone penetration test. So it's a cone, it's mounted to a truck, it goes in the ground, there's a lot of sensors, it generates data. It costs about $5,000 per point, per location. So we get this data, we feed it into models that predicts the triggering of liquefaction, the occurrence, at discrete depths, and then that data feeds into manifestation models. So these are models that try to predict the system response of the entire soil profile as manifested at the surface. So it's like damage potential. Okay, so one of these models is called the Liquefaction Potential Index, LPI. And people study case histories, they train fragility functions to predict the probabilistic consequences conditioned on LPI. So we have models to predict, you know, ground deformation, pipeline rupture, foundation damage, et cetera. So this is what we can do at site-specific scale. So the problem at regional scale is there is no data. And so our general strategy is to train surrogate models that mimic the predictions of high-order models using low-order information. So I'll explain what we do in 5 simple steps. So step 1 is to get all the geotechnical subsurface data that we can get. We're training on about 40,000 CPTs. I think the floodgates are about to open. The big problem is most of this enters the public domain in hard copy. So it comes through town municipal planning boards, it's hard copy, that's how we can get it. The language models can already digitize automatically, but it's not good enough. So on some timeline, we'll be able to train on millions of data points. Okay, step 2 is we take each of these tests and we subject it to a range of seismic loading, and we use our state of practice models to predict the liquefaction response. So we get this curve, and every site has a unique curve. So it's like a fingerprint of the site. And if we could predict this curve without going in the ground, we would effectively be predicting the liquefaction response for any earthquake that could occur. Okay, and so to that end, we fit the data with a very simple functional form. It's got 2 parameters. I'll call them A and B. So these are parameters that allow us to track the prediction of the mechanistic model. And so we're trying to predict A and B. Step 3 is to compile geospatial information. We start with a library of about 75 data sets. So some of these things are flashing on the screen. These are parameters of geology, geomorphology, hydrology, topography, climate, and they're all globally available. They're free. They're from existing maps, and they're from remote sensing sets. So these are all things that have some loose correlation to the subsurface. Step 4 is to train an AI model to predict A and B where we know A and B, and to then run this for the entire Earth. So it's computationally intensive. It's terabytes of information. It's billions of locations. It has to run in the cloud. The 5th and final step is to do geostatistical updating where we know A and B. And so here's an example on the left where we have the raw AI model of our prediction of our A parameter. This is near Los Angeles. Then we have a lot of geotechnical data where we know A and B. And we're doing updating so that the AI prediction is essentially anchored to reality. And so there's places where the prediction is scaled up, and there's places where it's scaled down. And so with this approach, the expected response is effectively pre-computed and stored everywhere on Earth. So we have these A and B maps, and they're awaiting information from a specific earthquake of interest. So within seconds of an earthquake occurring, we get the shake map, and convolving all of this, we can recompute this LPI index by way of our functional form. We can pair that with a fragility function, and we can rapidly predict some impact. So this is the probability of ground failure, meaning a certain kind of classification of ground deformation. And so we can do this at regional scale at high resolution within a few seconds of an earthquake occurring. We can obviously do it for any future earthquake too. And so all of the heavy lifting is done in advance. The end user doesn't need to touch data. They don't have to touch AI. It's super simple. So all of our stuff is on design safe. Design safe is like Git for natural hazards people. They don't like Git for some reason. So just to say a few things about what we're up to with this model, where we're going. We're getting this implemented, for example, in the USGS information products. So the public, when an earthquake occurs, they can see our products within a few minutes. We've run it for hundreds of scenario earthquakes in the Pacific Northwest, a couple examples here. We're doing network modeling in scenario earthquakes. So we're trying to model impacts to roads and bridges, and then putting in traffic models, trying to understand, traffic disruption can you get from critical facilities and so forth. We've developed workflows where you can take proprietary data. So there's a lot of proprietary subsurface data, and energy infrastructure developers are basically using this workflow to do site selection. So they're trying to decide, where should I put my big energy thing, right? It could be some kind of farm that does things, let's say. And we're developing analogous models for subsurface wave velocity. So this is to say, how will the subsurface change ground motions? And we're also making a model just like this to predict landslides in near real time. So thanks for the opportunity to share very quickly. I just want to acknowledge Morgan Sanger, who's the lead student at UW. So thank you.
Thank you, Steve. I like to start from grumpy to positive, although that looks scary. We can take one or two questions before we move to the panel and invite our third panelist. John,
I was curious. Hello. Oh, they ran. I was curious about the target of predicting within seconds of the earthquake versus, like we heard about in the previous talk, trying to pre-predict where the damage might be and then take preventative action.
Yeah, so the two use cases would be rapid response and scenario planning. And so both of them are equally relevant. They both have the same problem at broad regional scale. We can do it within seconds because that's how quickly the USGS is putting out what they call the shake map. All of the information is recorded at stations, it's interpolated, et cetera, et cetera. And so it can run fast. It can inform emergency response. It can inform the stakeholders. Where might my pipeline be ruptured? Where's my bridge down? But then for community planning and all of the different reasons for doing that, we can run scenario events. And so we obviously have ground motion simulations for all kinds of different scenarios. And so we do that too.
Yeah, that makes sense. Thanks.
Right.
Yep.
Thank you so much.